in this video, I want to talk about how we can go on and build this essentially, um, where we can move the game object around the world based on the navigation node or point. Let's say you have two objects here. It moves and go on and it moves, right? So one of the features that we have here as well is collision avoidance, but not really. Essentially, whenever it kind of overlaps, it will try to kind of push other objects around. So let's say you have these four objects here, and let's move a bunch of them through these points, right? What it does, it will try to go to the same location, and then but what happens is that once it reaches there, you kind of push themselves around, so that there won't be like two overlapping objects at the same location, right? So something like that, right? So as you can see, it moves and kind of push them around. Now let's try to move a bunch of them here. We have this nice, I guess, kind of formation behavior going on. And again, if they somehow accidentally go to the same node or position, it will try push each other around so that it won't be any more collision, and so on. In any sense, I guess I forgot to mention that what these red dots represent, the node or the navigation point where the object can move toward to or be on or be at. So this is actually very nice for RTS games or any other AI games that you might need to work on. But in any case, let's take a look at the script. But before that, let's take a look at what we have. So if you go to what I have here is a plane. I have a navigation system script attached, and then what this is just the how many nodes there are in the x coordinate, and then y not y z coordinate. So you can play around with that. For each unit, I have unit script, and we can change the speed, the radius of where, like how much collision you want to check, and then the amount of force that you want to push. Again, play around with that, and then you will see what I mean. But let's jump into the script. Before we go into A star, which is a bit complex, let's take a look at the navigation system. Okay, so what we have here is we have a navigation system class, where at the start we create bunch of cubes, right? As you can you just saw, we have x and y coordinate, not y z coordinate, and we just create the red cubes just to represent the node itself, and also we just generate the grid or the node that we're trying to build, the navigation itself, right? And that's that for the start. At the start, we just find spacing in between, and so on. Next one is the get closest node function. So what this does is that when you click, or any point in the world, there would be a relatively close node that you need to find. So again, the application for this is that when you click on something, right, anywhere on the plane, we want to find the closest node to that point, so that we can move that unit to that point, right? So how it kind of works out is that we just go through the grid, find the relative distance, or not relative, but the distance of the click to that, and that's it. And then once you find that, find the smallest distance, and then you just grab that node, and that's all it does. Again, this is used in the mouse click most likely, where when you move things around, you want to find which node it should go, right? Which position that the game object should move toward to. Now let's go to the node itself. Node, again, is the red cube for visualization point of view. We have an X and a Y coordinate. I guess it should be Z, but from my kind of point of view, I'm just looking from the top above, right? We have the X axis and Y axis, but in the 3D world, I guess that's a Z axis, so it's used differently. Parents. Later on, we will take a look at the A-star pathfinding algorithm, but what this does is it keeps track of where it came from. So in A-star, once you find the end node, what happens is that you want to kind of rebuild that path or reconstruct path, so that, let's say, you're going from A, B, C, and D, right? When you run the algorithm, it doesn't know really that it goes from A, B, C, and D. Okay. What it knows is that it's just trying to find the smallest distance that it can move to get to the end goal. But once you reach the end goal, what happens is that there's no such thing as going from A, B, C, and D, right? What you get is you have the D, which is the end goal, and then the parents would be C, right? So whatever came before that, C, right? What came before C is B, and what came before B is A, right? So this parent here is just to keep track of where it came from, so that in the end, once you find the goal, you want to rebuild the path so that you go from D to C to B to A, and then we reverse it, and then we get A, B, C, and D, which again we will talk about it in a bit. G-score is the cost from the start to the current goal. The current goal could be when we are trying to explore, and you will see later, but at the start it will be the root. Here would be the cost from the root or the current node to the target, in this case the end goal, so where we want to get to. And then F-score is the sum of those two, so the sum of the path from the beginning to the current node, and then the current node to the end. Okay. And here we keep track of where the node is, and it's just for debugging purpose. Okay. Now let's go to before we jump into A-star, let's take a look at the unit. Actually, probably easier to go with. We have your movement speed, push rate, how far you want to push, or giving the radius, how far we want to detect if that's something like nearby, and then the amount of push you want to push. At the start, we initialize the pathfinder. Then here we build we get the navigation system for each update. So what it does is, if there's any path, right, and the current index is less than the total amount, okay, the higher level kind of explanation is that at every frame we want to check if we're moving or not, right? If the object's moving or not, or if there's any node that we need to get to. So what this does is that from here, right, let's say you start at the root and you want to get to D, right? Let's assume the same scenario where we have A, B, C, and D. What this does is that at every frame we want to check, hey, has this reached the end yet? No? Well, then we try to move toward to that node that we're trying to get to. Let's say we start at A, right? We want to move to B. And so this is what it does. So it will try to move from A to B here, right, repeatedly until we get to the end, to B, right? So once the distance of the game object is close enough to B, right, we want to increase the index. So now from B we want to get to C, and this is what it does. So this whole thing here is responsible from moving from A to B, right? And then B to C, and then C to D, and then that's it. Once you get to D, we get to this, else if statement here, where we just reset the path and everything. And so the reason we have to reset is that, let's say you want to run it again. Let's say you want to move somewhere else. You want to make sure everything has not been cached or saved yet. Here we have a resub collision function where we just push, given the radius that we have, right? We create a overlap sphere just to check if there's anything surrounding us, right? So if there's another unit nearby or colliding or overlapping, then we will kind of want to gently push it away, and that is what it does here. Okay. Set destination. Here again, remember we talk about let's get closest node at any point in the world point. So instead we use a transform position. We want to grab the closest node to that point or to that position. Okay, same for this. So now what we have is we try to convert that world point to the node coordinate or the red dot, so that we know which is the starting point and which is the target point. Okay, we need to do this because the pathfinding algorithm we have requires that we pass in the node, the starting node and the end node. Okay, oops. And here we just call the find path, in which we'll talk here. Yeah, let's go into that. Here under the A star script, we have a star class. We keep track of which node that we have been explored here. Talk about it a little later. So yeah, let's talk about this find path function here. At the beginning, we want to reset everything just to make sure there's nothing in the explore node yet. And we have an open set and close set. Open set essentially keeping track of the nodes that needs to be evaluated or checked. Right, we need to go over the open set. Things that we need to check. Close set, things that we are done with. So we were done with that already. And we will see why we need both of them. G-score at the beginning. At the beginning, we assume the start is the root node, and so the G-score, the distance from the beginning to the root, which is the beginning, is obviously 0. S-score would be the distance from the start or the current node to the end node, to the target, right? So this would not be 0. And then at the start, we want to add the root node to the open set so that we can, here in the loop here, we can work with that. Again, the algorithm works by finding the smallest F score of whatever is in the open set and then explore that, right? So here, if the current node is the target, then obviously we're done, right? We want to rebuild the path, in which I just mentioned previously, but I'll go over it again. Then we want to reset everything, and we return the path. But let's talk about in general. In general, what it does is we since we're exploring this node, we need to remove from that, so we don't explore it again. And here we add it to the close set, so to that. And the reason why we need to add to the close set is that we want to make sure that if we explore the neighbors, that neighbor that we're exploring is not already been explored. Okay, we'll talk in a bit soon. But here we want to grab each neighbor, right? At the start, at the root, we grab the neighbors. And then for each neighbor, see here, we want to check if that neighbor has been explored or not. If it's already been explored, then we won't need to worry about it. So just skip it. But if not, which is usually the case, then we want to find the G-score or the relative score in that sense. You could think of this as a F score, because it's a current goal to the not really. Okay, this is a G score. Okay, so what's going on here is we want to find such neighbor that we want to move to. Okay, we want to find the good smallest distance neighboring node that we want to move to, and this is what it's doing. If we find that smaller distant neighbor, then here we set that to that, right? We set the G score to that, and then we calculate the H score from the current was in like the my bad. I guess I was just a bit confused. But yeah, so the H score again, remember, is the score from the current node, in this case, the neighbor, to the target, okay, which is the end goal. And then the parent again is where it came from. So in this case, it will be the current node of which we just was just looking at. Okay. And here we we check if the open set doesn't have this neighbor already, then we want to explore it. So just making sure we don't have a duplicate. And that's it. So this is repeated until until this condition is reached, essentially. Again, just to recap, what we're doing here is we for each iteration we look at the neighbors, find the tentative T score, right, the closest distance that it makes sense for us to move to. Okay, and then from there we want to set the G score to that. The S score would be again the node, the distance from that node to the end goal, and then where it came from. Rinse and repeat until you find this, or not. I guess it could be a case where you cannot find it, but most likely you will find it. Because in this we don't have any obstacle yet. But anyhow, at the end, once you find the target, or the current node is the target, that means that we have reached that goal. Okay. One of the best way to learn this is to look up A-star pathfinding algorithm and then look at the pseudocode and kind of write it down, like draw it, and that should help. That helped when I was trying to learn it. Here, reconstruct path. Long story short, you have, let's say you want to, you move from A to D, right? So A, B, C, D, right? What happens is that at the end of the algorithm, you get to D. Now what? Like how do you get the path? Well, one of the ways to get the path is to go back. So from D, right? D, C, D, A. Okay. So if you go back reverse, you will get D, C, B, A. But what we want is we want A, B, C, D. So what it does is it literally all it does is it go back one by one. So D, C, B, A. Then we get those obviously path of thing like D, B, C, A. And then we want to reverse it so that we can get from A, B, C, D. So that would be the path that we're trying to get, right? Because think about it, when you move an object, you want to move from A, B, C, D, not D, C, B, A, right? So so that's what we're trying to do here. So that's how we get that node, and then that's how we kind of move the game object along those nodes, right? Okay. Distance. I think there are two common distance functions. One is Euclidean, and the other one is Manhattan. In this case, we use Euclidean, which is just a square root of x squared and plus y squared. So take a look at the Manhattan as well. I think for Manhattan, you go from up, down, left, right. But here in this case, we can go to diagonal. So that's why we need a Euclidean. But again, and then obviously again, distance will change how your algorithm, not algorithm, but your object would behave. So maybe one of the things that you can try is to use Manhattan, right? Um, just to see how how the movement is different than Euclidean. Get neighbors. We have a node. We want to grab where find the where relative where the neighbors are, right? So and that's all that function this function does. And then reset everything once we're done with that. Yeah, I think that's pretty much what we have done in this example. We spoke about with Spirit Tracker before. We spoke about UI stuff before, so we're just gonna ignore that. Let's go back here again. Just to recap, you have an object here. You can move from A to B, right, easily. I mean, not A to B, but A, B, C, depending on how you look at the problem. But here you have 3 of them. You can move it around as well, and so on. I mean, I didn't figure. But you have 3 objects here. You can move all of them together, and then it will try to find the path to that point. Oh, I don't think I spoke about this before. So here, as you can see here, the movement is kind of nice and formation. The way I did it, let's take a look at it now. It's under the mouse, I believe. Okay, take a look at this. This is this one selection. I believe it's selection here. Here. So we have a formation position. So how it works is we kind of we calculate the center point, and then we get the top left, right, and then we just kind of increase that by some offset, and then the spacing too. And every time, I believe, every time we do that, we set the destination. So when you set the destination, remember that is I don't think we need this. Don't worry about this. Because so what happened here is that when you set destination, this function is already called. So this is no longer valid, I don't think. Set this destination, it will we get the row position, and then that will find the closest node, and everything should work out fine. So what I mean by that is every time here you select that, or let's say you can do more. You can select more of this. Let me try to restart that. If you select more of the game objects, click on that, it will try to find the center point, and then from that center point it will try to find the top top left node, and then try to get that world coordinates, and that world coordinates will be converted into a node coordinate essentially, right? So it will try to grab a bunch of nodes where relatively close to that whatever the world coordinate is. So that is something I guess I didn't mention, but I just want to talk about that quickly. So and then but that's how we get the formation kind of movement going on here. Right. Yeah, I think that's everything in this video. Thank you for watching. I hope this is useful, and you learned something from this video. If you have any questions, feel free to reach out. I will be happy to answer any question. Thank you very much for watching, and have a good day. Bye bye.